Hello. Good morning. How are you guys doing this morning? It's the last day of TechEd. It's 8:30 in the morning. You are the animals. You are the coding animals. You're the diehards, the hardcore, the guys that want to be here at 8:30 in the morning to learn mind-twisting things. We want to talk about, it takes a special kind, a special breed of developer to show up for an 8:30 talk on asynchrony. So I applaud you all. That's awesome. My name is Dustin Campbell. I am a program manager on Visual Studio, focusing on the languages. Actually, I work on Project Roslyn, which is about Visual Basic and C# futures. But I'm really here to talk to you about a different kind of future today, not that kind of future. So I've been around for a little bit of time at Microsoft and in Visual Studio, and I remember Async when it was in its infancy. So how many people have actually played with Async so far, with the await and the async keywords? Good, a fair number of you. That's good. So I was around when it was some ideas, and there were some prototypes, and I remember about 2 or 3 years ago, we said we were going to take some time and investigate and really try to reimagine what it means to do asynchronous programming on .NET. And we wanted to really make it simpler to be able to call APIs that return a result at some point in the future. Now, as we do at Microsoft, that meant that we started up some working groups. We had some design meetings, a bunch of design meetings. We had super smart people thinking super smart things. And what we eventually landed at was a combination of new APIs and patterns for the base class library, and a complementary set of language features for C# and Visual Basic to make it easier to consume those. Okay? Now, at the same time, this is during the Visual Studio 2012 development cycle, which is still going on. Though we're almost done. RC's out there. At that same time, we were focused on something else very important, and that was Windows 8, right? And more specifically, the Windows runtime, where we had a lot of work to do to make sure that C# and Visual Basic can call into the Windows runtime APIs. So, but it's no coincidence that today I'm here talking to you about async and the Windows runtime together, because the Windows runtime has taken a huge bet on asynchrony. Okay, and that's kind of an important thing. So you've got .NET sort of thinking about asynchrony. You've got Windows runtime thinking about asynchrony, and if you look at JavaScript, you know that the APIs that you would call to do network requests, those are asynchronous APIs. So what's the big deal? Why are we dealing and thinking about asynchrony so much? And the idea here is that this is all for the purpose of not blocking threads. Okay, we want to write applications that don't block threads. And that helps out on both the client and the server. So on the client, this gives you responsiveness, right? For example, many client environments require you to do certain amounts of work, certain pieces of work on the UI thread. So for example, in a browser, if I'm doing JavaScript or a Silverlight application or something like that, I can only make network requests on that one thread the browser gives me, right? So if I did my network request as a synchronous call, then that happened to take 10 seconds. Well, that's 10 seconds that my user is sitting there waiting, and my thread is blocked, and I can do no other work on that thread. And 10 seconds is an eternity, right? So that's bad. Now, on the server, we care about scalability. So you've got some number of threads they're listening for incoming requests. And if, for example, maybe my application, in response to those requests, calls out to a web service and waits for that response to come back. Now, again, if that's done synchronously, now I'm blocking a response thread. It can no longer take incoming requests. And, I can run into a big scale problem. I can be a bottleneck to that, because these things could just be sitting there spinning. And threads on the server, they're not free. They're by no means cheap. And so that can be a big problem as well. So really, as this keeps on going, as these problems come up, synchrony is really becoming the norm, the common solution for this problem. So to be able to call an API with a callback that gets called at some point in the future when an operation completes and provides a result. So you could actually do this manually, but the industry's moving forward to another more modern abstraction about kind of around the same thing, and that's called futures. So a future is a first-class object that represents a piece of ongoing work. So if you've used LINQ, you know that IEnumerable is sort of the common currency that you use when you're dealing with LINQ. When you're doing asynchrony, these future objects are kind of the common currency when you do asynchrony. And then being able to reason about these futures, treat them as first-class objects, combine them together in interesting ways, that makes it it's a very powerful concept, and it's very, very powerful when you're designing APIs to deal with them. So as we're doing all this work, we're doing all this thinking, and independently, the .NET and the .NET languages are thinking about asynchrony. Windows Runtime is taking a bet on asynchrony for its future, and so what ended up happening is we have two different APIs sets. There's the .NET Async and there's the Windows Runtime Async APIs. And so they're different APIs. They are, in the details they are different, but they're actually more similar than they are different. Now, since build, we've actually, we've taken a lot of feedback since the developer preview came out in build. We took a lot of feedback, did a bunch of iteration on this, and today they're actually much more close than they are distant. We've drawn them closer together since build. And so we're going to talk about some of the differences and similarities and how we've brought them closer together in this talk. All right, but first, I want to get on the same page with what I mean by synchronous and asynchronous APIs. All right, so I've got two sets of code up here. The first one is synchronous, and what it does is it calls a function called download data, gets back the result of that function, and then passes it immediately to another method called process data. And so the way I like to think about synchronous methods, or synchronous APIs, is that when I walk up to a synchronous API, I want the data so I can do the next step with it. Okay, that's how I kind of think of these things. The asynchronous version on the bottom, it calls download data async, and instead of getting back the data, it immediately gets back a future object. Okay, and that represents the work of downloading that data, and it's a future that at some point that data will be there. And so now it comes back immediately, and I can register a callback on that, and that's the continue with method, where I say future.continue with, and I pass an anonymous function, a lambda, that says when the data comes in, do this next. So if I think of synchronous APIs as saying, give me the data so I can do the next step, I think of asynchronous APIs as saying, give me an object that I can tell what to do next with the data. Okay? Now, let's take a look at this from kind of the perspective of what happens on the thread that these execute on. All right, so in the synchronous API, we call download data. That takes just a small slice of time on the thread. And process data happens sometime later. But in the interim, it's completely blocked. The thread is waiting for the result. And I want to be really clear here. This isn't that my CPU is doing work. I mean, this is actually this is a network request, right? So that means that, I'm calling into the OS, I'm making a network request, that goes through a socket, comes out to a server, waits for that to download data, comes back to a socket, wakes up, tells the OS that there's data available. The OS figures out that's for me and comes back and gives me my data, and I call process data with it. So I'm actually sitting there waiting for and doing nothing at that point. Okay, I'm just blocked waiting for really not a lot of value. Now, on the asynchronous version, it looks more like this. Okay, so I can do download data async, and then it returns immediately to me, and I get called later when the data is available. So what's great about this is that, now imagine these are my UI threads, right? So in the first one, if I'm trying to move the application around, scroll with the mouse wheel, click, nothing happens, right? In fact, I'm probably going to get that little not responding at the top of my application eventually if I keep on clicking at it, insisting that it do something. Because it's blocked, it's waiting, it can't pump any of those messages to handle any of those events. But in the asynchronous version, at this point, it is free to handle UI events. So I can click, scroll, move it around, and everything works as expected. So, I mean, some of you have probably seen applications where you do that, it starts doing some long-running operation, you start clicking and then you're like, oh man, this is just broken. And all of a sudden, at the very end, it resolves, and all the events just bunch up at the very end, right? That's bad. That's not what we want our applications to do, right? Okay. Now, this gets more severe if I need to do two things, right? So suppose I have two downloads that I want to do. Now, if I have a single thread and it's my UI thread, I'm blocking twice. I have to do them serially, right, on the synchronous version. But with the asynchronous version, I can just do one after another, let them run in parallel. And if I don't care what order they come back, and they might even come back in different orders if one happens to be in a different order if one happens to be faster. All right. So that's great. You're probably thinking to yourselves right now, other than the fact you're thinking, man, it is 8:30 and we are talking about this. But you're probably thinking to yourselves right now, well, that's great. The API is great. Why don't I just use that? Why do I need language innovation on top of that? And there's a very good reason. Right now, this is a pretty simple example, and already the bottom bit of code is kind of complicated, right? I mean, it's not really that complicated, unless you have like an aversion to like Greek letters and lambda expressions, and there are people that do. But it's certainly not as simple as the sequential code right at the very top, right, where it's just one statement after another. My control flow is obvious. I can reason about it, right? Instead, I'm hooking up lambdas. Now imagine, on the bottom example, imagine that process data returned something that I wanted to go, maybe it returned a URI, that I wanted to go download something else, right? And I wanted to do that asynchronously. Well, now I'm nesting a lambda inside. And now imagine that came back and wanted to do something else asynchronously. And so I start getting into this nested lambda hell, right? Has anybody ever experienced the nested lambda hell? Yeah, I see guys are nodding their heads. They've got bruises and they're wearing bandages from nested lambda hell. So when you abuse gotos, we call it spaghetti code, right? And what I've heard that makes a lot of sense to me, the way I've heard this described, is that when you get into all these little nested lambdas that are just these kind of little nuggets of functionality chained together, call that macaroni code. Think of it like a string with macaroni just all connected together. And it really kind of obscures your control flow. It makes it harder to maintain. So you gain a lot from doing asynchrony, but it makes your code more difficult to maintain after the fact. So, C# and Visual Basic. C# 5 and Visual Basic 11 let you do asynchronous programming without callbacks. So, the new async and await keywords, they let you do asynchronous programming simply by, generating the callbacks for you, telling the compiler, giving the compiler some clues that, hey, this is a magical moment where I want you to do heavy lifting for me. All right? So, with async, you can actually just write your code sequentially, like the first example, and the compiler will essentially transform it to the second example. All right? So I want to kind of dig into an application that I've got. This is a Metro style application. It's already using await and async, so it's already asynchronous. But I want to kind of drill into it and explore it a little bit, see how it works, and then let's see how we can kind of explore how we can make some changes to it to make it a little bit better. All right, so I want to F5 this application just to kind of show it off a little bit so you know what we're working with. This is a pretty simple application. It's based on one of the default templates, and what it is it builds photo mosaics. You've probably seen these before. They're where you have a target image, and then you have a bunch of little tile images that you can do some number crunching to kind of figure out based on the shape and the color of these tile images. You can assemble the target image, or at least an approximation of it, so that if I'm standing far away and I squint at it, it sort of looks like the original target image, but if I get in close, I see all these little tiles. And the way we do this is we have here a list of Flickr tags, and when I click on one of these, it'll ask me to grab a target image, and then it will go out to Flickr, use a Flickr web API to download tile images that it's going to use to construct that image. All right, so I'll go ahead and click here, and I've got an image of a good buddy of mine, mostly his wide gaping open mouth. And so it's downloaded images, and now it's calculating the mosaic. I want to point out that this is actually a responsive app right now. It's doing the calculation, but because I'm already using await and async in here. All right, so that's what this does. Let's flip back and take a look at it. All right, so most of my logic is in this item click event handler. This is called triggered when that list view on the left is clicked, the list view of Flickr tags. And so if you're familiar with XAML programming, this is really, this should be pretty familiar to you, most of this code. So the first thing I'm doing here is I'm actually just groveling into the event args, pulling out my model, making sure that it's selected in the UI, figuring out which item was clicked. Then I update some status text. And then here, I new up this type called a file open picker. Okay? And this, if I look at the type of this, I'm going to hover over var, and you can see that the top level namespace this comes from is Windows. So this is one of these Windows runtime APIs that I can now call from C# and Visual Basic, and you'll note that it looks just like a regular C# and Visual Basic type. I can use an object initializer with it, set a couple of properties, give it a file type filter so it knows what to look for, put it in thumbnail view so that when I'm looking for those images, I can see Drew's handsome face. All right? Now, the next thing that happens after I've constructed that is I call this method pick single file async, which uses the open file picker to let the user choose one image from, I guess, from the operating system. That could be from the file system. It could be from SkyDrive. There's a lot of places this could come from that the user could pick it. And then it returns a storage file, a Windows RT storage file. Now, this is an asynchronous method, and I can see that there are 3 clues that tell me it's an asynchronous method. First of all, it ends with the suffix async. That's it's kind of obvious, right? It's a recommendation that you guys, if you're creating async methods, to follow this convention of putting async at the end of it. That way, so that when you're looking at your code, and maybe you're not awaiting it right away, maybe you're not awaiting this async method, but you're getting the future object back from it and doing something else with it. So if you're just looking, you can tell which methods are async, are doing asynchronous work, potentially. So it also says in the tooltip, it says on the far left of that tooltip, it says that it's awaitable, which means that this method returns one of those future objects that I was mentioning earlier that I can now await on in my code. And then finally, it returns a type. It returns iasync operation of storage file. Iasync operation is one of those future types. It's actually one of the WinRT future types. Okay, so this is a WinRT asynchronous API. It comes back with a future type. So if this is coming back asynchronously, well, I need to wait right here in order to get the result back, because I'm going to use it on the next line. Right? I'm going to use this on the next line. So if I were doing this manually, I would get that future object back, and I would hook up the callback. And the callback that I'd want to hook up is really just the rest of the method, right? That's what I want to say. When you're done, when you get this back, now continue executing my method. So essentially, I want to get to the place where I'm pausing and resuming this method. And I want to make sure that I'm doing it on the same thread. Await will do that for you. So if I'm on the UI thread, using await will pause the method, register the rest of the method kind of as a callback, return immediately, and then when it comes back, it'll execute it in the same context. So if I'm on the UI thread, it'll execute on the UI thread. If I'm on a background thread, it'll execute on another background thread, just so that I have the same kind of semantics of the original context. Now, this is kind of cool, right? And what happens here, in fact, yes, when I call await here, it simply returns. It's done, right? Now, the reason that can happen is because I put async up here. That's kind of the magic that tells the compiler, hey, make sure that you can chunk this method up, right? Do all the magic and things so I can chunk this method up into pieces that make it awaitable, so all these await points can be captured. All right? So next up, after I've picked a single file async, I come and I open it async. All right? Again, I'm calling through the Windows runtime and getting back a iasync operation of irandom access stream. So await again schedules a callback, and when I get back, I don't get back the operation, that iasync operation. Instead, I get back the irandom access stream that I can then take and manipulate and work with. Okay. The next piece simply is, if you've done XAML work, you know, this is just creating a bitmap image, loading the bitmap image, setting it in UI. There's nothing special there. However, this next bit of processing is a little more interesting. There's a bunch of stuff that happens here. So first, this is just a synchronous API to kind of compute the Flickr API I need from the Flickr tag to go out and do my query for tile images. The next bit calls into, it constructs this object called an HTTP client. All All right, and this is something coming from .NET. This is actually part of the new HTTP API that replaces Web Client in .NET 4.5. And then I call getAsync off of this, and so it's going to go out and do my HTTP request in an asynchronous manner. But this is a .NET async method. So instead of this async operation, this future object that we saw from WinRT, this time it's returning a task of HTTP response message. And that task is the future object for .NET. All right, so you see that it's awaitable, and I can await it. Now, what's cool about this is that I await this in the same way that I awaited the WinRT objects. Okay, the WinRT operations, it works the same way. So I can use these interchangeably and have a unified programming model, right? So this really solves a ton of these kinds of this problem where sometimes I'm talking with .NET, sometimes I'm talking with WinRT, and most of the time you don't need to care. Okay, it just works. You can just use await. All right, next I'm going to go ahead and read the string as async. This is the sort of thing that, you know, I see a lot, especially as we're doing Windows 8 programming. We want to make sure that our apps remain responsive, right? And so some of these things that might take long, we try and make asynchronous. So, for example, if I'm resizing an image, the APIs to resize images are async because they may take longer than 50 milliseconds. And that's kind of the guideline that if you're doing a long-running piece of CPU-bound work, you want to make sure that if it's 50 milliseconds that you do that in the background so that your app remains responsive. Okay, so I call this read as string async because the string might be big. Then we call our little synchronous helper API that parses that XML and returns the list of photos. And then finally here, well maybe not finally, but I go ahead and I fetch those images in an async manner. Now, this also goes out and it will. This is a helper that's in the application, but it'll go out and it will download images that it doesn't already have cached. So it does some caching so that my demo doesn't download thousands of images while we're waiting here. And then the real work. Now we've got the two pieces we need. We need an original file up here, the actual target image we're going to create a mosaic for, or of, and then we need the list of tiles. So now that I have that, I can create my mosaic. I've got an async method to do that I await. This returns to me a storage file, just like the open file picker. And so then I can open that storage file async. I can create a bitmap for it, just like I did before, set it in the UI, and then I'm done. All right? So that's the application. What is awesome about this, and I mean it is awesome because this would be crazy if it weren't this way, is that my event handler is written sequentially all the way down. Just one statement after another, naturally. I can reason about this control flow. It all happens on the UI thread. Okay? Everything here comes back, in this event handler, comes back and executes on the UI thread. So I get an implicit lock. So if you're thinking, well, how do you deal with resource contention? Well, you're always on the UI thread. That's why people do things always in the UI thread, so that they get that implicit lock so they don't have to think about resource contention. I get that same behavior here. Okay? This is pretty cool. I'm looking at this and I'm thinking, you know, there's probably some changes I could make to make it, and it's getting a little bit long, right? That's something I should probably change. So let's go up here. Let's take this piece of code where we actually get the user to choose a source image, and let's extract that to a method. I'm going to actually use the built-in extract method refactoring. Some of you may have tried that prior to the RC and found that it was not working that great with async. And so we've invested in that since the beta and really improved extract methods so it can do so that it can extract really great async methods. So the extract method that I'm expecting, well, first the only thing that's in this selection that escapes this selection, that escapes this and is used later is the original file variable right here. And then because there are weights inside of there, it also needs to become async. All right? So I'm going to go ahead and I'm going to right-click, choose refactor, extract method. We're going to call this create source image async. And you see that from the signature it's producing here, it is going to create an async method, which is great. And remember I said that the original file is the only piece that escapes, and that's a type storage file, right? But because this is an async method, it makes sure to wrap that in a task. It's going to create a future object for that and to pass back. So I'm going to go ahead and execute this so we can take a look at it. It's right here. So yeah, as you can see, this now returns a task of storage file rather than just storage file. That's part of being an async method. You can have, there are kind of two kinds of async methods. There's a kind that returns void, and then there's a kind that returns a task. And so the void kind right here, this is an event handler. And the problem with an async void method is that, and why you should only use them for special cases, is because you can't await them. There's no future object that comes back, so you can't await them. You essentially are saying, I don't care when this completes, which is perfect for an event handler, right? Because the way this event handler works is that, the user clicks on that list, that puts a message in the queue, the XAML of the XAML UI stack, the message pump comes along, handles that message, calls my event handler, and then all the XAML UI stack cares about, all the message pump cares about is when it gets back control so that it can continue to pump messages, right? And so because I've now said in my event handler, I control the flow, and I'm going to release at all of these await points for the message pump, that's how I get my responsiveness, right? And that works really well to have an async void method for the message pump. However, for helper methods, I want the caller to have control over when this completes. Okay, and so in order to do that, I need to return a future object that they can manipulate, they can reason about, they can await on. So what happens when I hit this first await? Well, the same thing that happens when I hit the first await in the event handler. Remember, in the event handler, we just return immediately. We return immediately to the message pump as I just described. However, when I hit the first await here, that's not quite what happens. I mean, it's close. We return immediately. However, the compiler constructs for us behind the scenes a task, a storage file, this future object, and passes it back to the caller. So that's what gets returned. So that the caller can then go ahead, register callbacks, with the await keyword on the other side, and keep things rolling. Now later on, when I return here, returns inside an async method are a little bit different than a normal return. This doesn't actually just return the original file object. Instead, it goes back to that future object that was originally returned at the first await. It sets this as the result, and it signals completion. So then the await on the other side can go, okay, my callback's going to run now. Does it make sense? Okay. It's hard to explain these things at 8:30 in the morning. All right. Now, we've been talking about returns. And that's one way, that's a very common way to leave a method. But there are other ways, right? Maybe by an exception. I mean, exceptional control flow is something that is important to manage, right? And so exceptions could happen. And in fact, in this method, I have two async methods, two awaits where an exception could happen. On the second one, that open async, I mean, what if this was going off to SkyDrive and somebody unplugged the network cable? Well, now it's going to throw an exception. And how's that going to manifest itself in my code? Likewise, this could throw an exception. In fact, I'm going to introduce an exception here, just for us to laugh and giggle at. This is something to know about the file open picker, but if you don't actually specify the file type filter, it will throw, because it doesn't know what files to show. So I'll just go ahead and comment that out so that we can get an exception to occur. And what happens when an exception occurs is not that it actually gets thrown, because this is coming from WinRT. This is a different universe. This is not coming from .NET right here. Instead, the iasync operation, which is very good at giving us back results, it's very good at signaling completion, but it's also very good at tracking exceptions. All right? So the iasync operation comes back to us, and it gets set to an accepted state, which await then unpacks and resurfaces the exception. Okay? Now, that means that now I can put a try catch right here. The catch block, the await would know to, okay, pass that over to the catch block, and everything would be fine. But there's another way to deal with exceptions, right? And that's to just not deal with them at all, right? We could just ignore them, let them bubble up to a higher level, maybe to my caller, because maybe there's a helper method, and it's an exception that's totally reasonable and could happen, and it's my caller's responsibility to handle it. Well, in that case, if I let it go, then it gets wrapped up, it gets set on this task of storage file that I'm returning, and so that gets returned in an accepted state. Okay, back to my caller. And what's really cool here is that I've now taken an iAsync operation, an exception from WinRT, transformed it into .NET, and I'm now wrapping it up in a task. So these things just kind of bubble through naturally. Again, you don't really need to worry most of the time about which ones you're dealing with, which future objects you're dealing with. So now it's going to bubble up back here. That's going to, again, unpack and resurface the exception. And now if I want to handle it, it's easy. I just use a try-catch. And this is the sort of thing that if I started doing this with lambdas myself, gets really, really nasty. Handling exceptions, handling errors gets very, very nasty. So I can say, okay, status text equals, oops, an error has occurred. All right? So now I put in my error, right? So that's going to happen when my open file picker is started. So I start my application. Click on this guy, that's going to cause the open file handler, and hey, it works. Exceptions work. All right. Cool. So this is the sort of thing that, like, we've really worked very hard so that your code, the sequential code flow, the code that you're used to writing, continues just to work with asynchrony in the async feature. So if you use loops, if you use if, those are, again, things that become very nasty when you try and do this yourself manually with lambdas and callbacks. Those just work here in async. Okay? And that's, it's magic. It's absolutely magic. So let's go ahead and let's fix our errors so that I don't run into it later. All right? And there's some other things I want to do here. So for each of these future objects so far that I've gotten back, all I've done is immediately await them, right? It's very, very simple. I have a very, very simple pattern here. But these future objects are themselves very powerful. They're first-class objects that I can use. So what if I wanted to, instead of awaiting it immediately, I'm going to go ahead and transform this, take away the await. We'll call this original file task because it returns a task of storage file. Again, that's and what's cool about this is that's a task, a .NET task of a WinRT object. Okay, again, just mixing and matching things. So I can come in here now and I can say original file, whoops, await my original file task. Now, of course, that's lame, and you guys are all sitting there going, wow, that's exciting, Dustin. You have moved it to the next line. Okay, it is kind of lame. But what's really cool here, and you might not have even seen it yet, is that this original file local is only used in one place. It's actually it isn't used until down here. Okay, and so what I can do is I can move that line, right? I can move this line all the way down right before I'm going to use that because none of this processing depends upon it. Okay, and the way .NET tasks work is that when you get a .NET task back from an API, it's already operating. It's already in flight. It's already doing its work. And so by moving the await down there, I actually get implicit parallelism because it starts downloading the tile images at the same time. Okay, cool. So let me F5 this and just kind of give you just prove it to you. Now, the way this is going to work is I'm going to click this, and if you watch in the middle, you're going to see that download tile images appear just kind of a flash before I get over to pick Drew's handsome face again. Okay, do you see it? It's very, very quick. All right, I'm going to pick Drew's handsome face. I actually have some time here. I could, I could sort my single image by date or whatever. And all this time it's downloading those tile images while the user's interacting with this. Okay, so when I come back, it immediately starts creating the mosaic. It doesn't start downloading the tiles. It now starts creating the mosaic. And so not only have I made my app, a little bit more responsive, a little bit smarter, but I've introduced parallelism such that it's actually made my app faster, right? Especially to the user. All right. That is especially cool. Now, you can also do that with iAsync operations with WinRT features. So let's go back down here. And we'll do kind of the same transform. iAsync, original file operation, and my lame little next line, await. Oops. So, yes, again, Dustin, exciting. And in fact, this one's even worse because I can't move it down, right? It's used on the next line. However, this allows me, suppose I had more work that I wanted to do in this method, I can go do that now. So let's simulate some work. We'll use one of the task helpers. We'll use delay to create for us a task that's going to delay for 5,000 milliseconds, and we'll await that here. And what I want to point out right now is that I have interleaved WinRT operations and tasks, and it doesn't matter. Okay, I've got a WinRT operation that's spun up. I'm awaiting a .NET task, and then I come back and I await that WinRT operation that had already been started. So you can interleave these without really thinking about it too much. Now, there are times that you do want to know, am I dealing with tasks and am I dealing with operations? In fact, at the build time, back during the developer preview, there were a lot more of those times when you needed to think about and remember know exactly what you were dealing with. Because in .NET, we have this concept of hot tasks. I mentioned it a moment ago. And at build, there are kind of some fundamental operational differences between WinRT operations and the .NET hot tasks. Hot task means that when I get that .NET task, it's already started. I can assume that it's already running and already going. But at build, sorry, I keep saying build time, which might mean something different to some people. At build, that wasn't the case for WinRT. In fact, you got an operation back from WinRT. If you didn't await it right away, you had to call start on it. It kind of started cold. So if you wanted to kind of kick it off, you had to call start. And so that actually produced some subtle bugs in this case, because in this case, the operation wouldn't be started. We'd await the task, and so then it wouldn't actually start the operation until we awaited on the next line below the task delay. Okay, and you get some subtle bugs like that. So the way to fix that at build in the developer preview was just to choose, say, start as task. Okay, and but that's not necessary anymore. So since build, we made changes to the WinRT so that the WinRT operations are also hot. They have the same kind of hot semantics like the tasks. So you can really use them simultaneously. And let me kind of show you some of the benefits to kind of show you what this looks like. I'm going to use the debugger. Some people have been asking us, how does async look when I'm in the debugger? What do you guys do? We took a lot of time to kind of think about that and kind of figure out what does it feel like when I step around. And hopefully, if we did our jobs, it works like you think it should, and you don't ever notice it. So I'm going to come in here. I'm going to click on this, which should hit my breakpoint. Okay, that creates my open file picker. And then if I step, and I step again, well, at this point, that operation is already running. It's already trying to show the open file picker. Now, because my message pump hasn't run yet, because I'm in the debugger and I've stopped the whole thing, it's not showing. However, if I step over this await to task.delay, then I come back and it immediately starts showing because it was hot. It started running immediately. And then as soon as my 5 seconds are up, I'm back in the debugger again. Okay, stepping. And so then when I step here, now I'm awaiting the open file picker, and so it comes back and says, okay, it's time to go ahead and pick. And I pick, and it stops again. All right? So that's kind of how the debugging experience works, but that's also kind of showing how those hot tasks really are beneficial. They can really get things going and kind of get things in motion, get the ball rolling where you're doing asynchronous work. Now, you can still wrap a WinRT operation in a task. We use start as task to wrap it in a task and automatically call start before. But if you want to still wrap it in a task, and there are good reasons to do so, we'll look at some in a little bit. It's just like that. Okay? And so that's going to give me back a task that manages, kind of wraps around my async operation and manages that for me. All right. So let's head back to slides. So async makes your method asynchronous. So we saw that the async keyword, when I put it on a method, it tells the compiler to chunk my method up, to prepare to kind of let my method be broken into chunks with the await keyword. Under the covers, the compiler is actually producing a big state machine, a very ugly state machine, but one that you don't have to worry about. It's similar to how iterators are implemented under the hood, but you don't have to worry about it. Instead, just write sequential code flow and let the compiler worry about it for you. Okay? Now await makes the rest of your method, into a callback. So within a method that's marked as async, each await point causes the rest of the method to be packaged as a callback for that particular future object on which you're awaiting. So now, and just to kind of drill it home again, it doesn't matter what sort of future object you're awaiting. A WinRT, .NET, they kind of operate the same. And there are actually other objects that you can await as well. So you can await F-sharp async objects. So if you want to be the F-sharp future object, so if you want to do use the F-sharp actor library, for example, from C# or Visual Basic with await, you can do that. You can also create your own awaitable objects. But one thing I didn't mention earlier, but I do want to kind of call out, is that task is special. When you're creating an asynchronous method in .NET, in C# or Visual Basic, task is very special. And so any async method needs to return a task. So if you have your own awaitable object, you're going to have to wrap it, either wrap the task or do something else. But it's certainly possible to do so. Okay. So at the Windows Developer Preview, this is kind of what the state of the world was. These were our big awaitable future objects. On the .NET side, there was task and task of T-result. Task is the one where you don't care about the result, and task of T-result is the one where you do. And then the analogs for that on the WinRT side were iAsync action and iAsync operation of T-result. Now, the key difference of these guys was that, like I said before, the .NET tasks were already running, okay, but the WinRT operations had to be started. And so that really impacted the sort of operations you could do with them. So you could await them both directly, right? Because and we would implicitly start that WinRT operation. However, because we had to implicitly start it and we had to hook up a callback at that point, we could actually only await it once, and it threw an exception if you tried to await it multiple times. Whereas on the .NET side, it's no problem to await these multiple times and that's the behavior you want. You want to be able to say, the first time you await some future object, you want to go off and do the work and finally return the data to you. The multiple times afterwards, you want to just get back the data that it's already calculated, right? And so that can be a very natural way to do things, especially if you're working inside a loop. But that was a problem with WinRT operations. It was very difficult to work with them like that. You can also store a task later and await it later. But if you want to do that with a WinRT operation, you'd need to use start as task. So since then, things have gotten a lot closer, as I said. And so now they're almost the same. Very, very, very similar in the operations you can run. You can await them both directly. You can await them both multiple times. They're both already running. You can store and await them later. Or for a WinRT operation, you can also call as task and await that later. Okay. So this is the world today, and it's a much sweeter world. Another thing we mentioned was these two types of async methods. There's the task returning version and the void returning version. And as I said before, the big difference is whether or not that method can be awaited. If it's a void returning method, it can't be awaited. So it's more of a fire and forget style of method. And so that's really used to start some independent code flow, independent control flow, where I'm responsible for managing my flow. On the other side, for task returning async methods, those can be awaited, and those are about giving control back to the caller so they can determine when you should complete, and they care very much about when they get things back. So the async void works very well for event handlers and for certain void contracts, right? I think it even says up here, when you override a void method and you want that to be async, for example, is a great time to use async void. But for helper methods, library methods, we always recommend you return task. All right, so we've seen some simple cases of flow and how control flow can be made asynchronous. But with these future objects, we also saw how we could do implicit parallelization, which was pretty awesome, right? Just by moving some lines around, by taking and separating the kickoff of a task from its await, we could really do some cool things with that. And so let's take a look at some more explicit operations that I can do with these future objects. All right? Okay. So we're back in our application. The first thing I'm going to do is I'm going to remove my important work. There's no reason to wait 5 seconds for nothing. Okay? Now, so far, everything we've done, everything in this method effectively runs in the UI thread. Right? It all goes off, does this async thing, hooks up a callback, and that callback always comes back on the UI. So, but what if I've got something that's long running, that's CPU-bound work? A lot of these are network-bound, I/O-bound work that happen where we're actually waiting, where we're waiting on some device to bring back data to us, some device or some other computer. What happens if it's actually CPU-bound work that I should really be doing in the background? Right? It's more than 50 milliseconds. What happens if for example, let's say I profile this application and I find that this piece of code, this line right here, is a bottleneck. Right? Maybe I'm on a device that's not very powerful. I mean, it should be fast, but maybe my device isn't very powerful. Maybe it's coming back with much more XML than I expected, something like that. So I could do this today. I could put this on the background. I could do this, I can new up a thread, hook up delegates, kind of figure out when it completes, do some nasty work like that. Or, and this might be something that some of you guys are familiar with when you do this sort of work, you could make all of this on the background, and then you could just poke back to the UI thread, right, when you want to update the UI. That's a common pattern that's happened over the years. But it just seems kind of contrived for the situation. I mean, I've just got this little nugget of functionality. Can't I just put that on a background thread and await that? And the answer, of course, is yes. Right? So I can wrap this up in a call to task.run. Task.run takes a Lambda expression, or delegate, and it executes that on a thread pool thread. And so then I can just await that. All right? And so now I've taken this piece of CPU-bound work and I've pushed it onto the background thread to keep my application responsive. All right? Just to show you that I can, what happens if this Lambda expression actually wants to do more asynchronous work? For example, maybe it has one of these crazy important pieces of work to do. Right? Well, in this case, I get an error, all right? But the error says that the await operator can only be used inside of an async Lambda expression. So I should add the async keyword. And just to show you guys that you can do this if you need to, this is sort of like a little void async method right here. But I can put async on a Lambda expression, all right? So I don't want to do that. I'm just going to pull it back. I just did that to show you guys. All right. Now, one other combinator that I really want to show you guys is task.whenAny. In prior demos, you guys might have seen task.whenAll. And task.whenAll takes a params array of tasks, and it returns a task that is completed when all of the tasks that you pass to it are completed. Task.whenAny is different, right? It's the one that when it returns a task, you pass it a params array of tasks, and it returns a task that is completed when one of the tasks that you've passed to it is complete. Okay? So I want to do that. I'm actually going to use this to, to do a soft timeout. And I want to point out also that these combinators like task.whenAny, task.whenAll are a great reason why you would want to use as task on a Windows RT, Windows runtime operation. Right? Because you want to be able to, if you want to be able to pass those into that combinator and treat them like tasks and use those combinators, you need to convert them to tasks and wrap them. All right. So what I'm going to do is I'm going to do kind of a soft timeout because this guy can take a long time. Right? He can take about 6 seconds, depending on with the image that I've got right now. Maybe it could take 10, 20 seconds, depending on the size of the image. So it's kind of it's one of these situations where my app is responsive and you can scroll it and you can do all this goodness. However, to the user, it doesn't look responsive, right? They may think it's actually hanging because nothing is happening, right? So I'm going to do a soft timeout where if 3 seconds pass before this is done, it'll kind of update the status text and say, hey, we're still calculating, all right? And the way I'm going to do this, I'm going to do this with task.whenAny. But first I'm going to do the same transformation I did before, where I'm going to go ahead and remove my await, and I'm just going to get the task back so that I can use this first class object as an object. All right. So down here we'll say mosaic equals await mosaic task. And now I'm going to create a task to represent my delay of 3 seconds. Okay? And I'm not awaiting this because I want to pass it to when any, which is going to do the work when this completes. So we'll call task.whenAny. We'll await that, task.whenAny. And we're just going to go ahead and pass my mosaic task and my delay task. All right, now remember these tasks that come back, these future objects, they're first-class objects, so I should be able to do things with them that I do with regular objects, regular normal objects. They should work as I expect. So I should be able to do, for example, reference equality. Right? So I should be able to say if the first task that came back was the delay task, let's go ahead and update the model status text to say still calculating. All right? Now if I F5 this, we can run our app. Click on here, pick Drew's terrifying face. And so now it's calculating the mosaic, and as soon as those 3 seconds hit, that task completes. It says it's still calculating. And of course, mosaic is still going on, and something is awaiting that afterwards. The mosaic task is still operating, and so it hits that await afterwards, and it says, okay, now I'm done. All right? So task.whenAny is actually really, really powerful. You can do a lot of stuff with it. I've seen things where people use it for throttling or something. For example, maybe I've got 10 downloads that I want to do, and so I go ahead and put it in a loop. I put all the downloads in there, and as soon as one of them completes, I go off and start processing that, and then do a task.whenAny with the same list, but with that one removed, right? And do that sort of work. It's pretty interesting. Some of the things that you can do with this is very, very powerful. All right. Let's head back to slides. So task. So the task type is, like I said, it's the future kind of object, the future type of .NET. And because we built these combinators around task, it becomes like a more general type that you can use to coordinate activities. So here's some of these helpers here. Some of these we've already seen. Task.delay just delays, gives you a task that delays for a certain amount of time. Task.yield is sort of its younger sibling, and what it does is it sort of yields for the minimal amount of time. Maybe it just allows a few messages to pump or whatever. But the idea here is that you can just use it to let your application breathe if you need to. For doing background work, task.run will execute your work on a thread pool thread. And then these last two for parallel composition. So if I want to do explicit parallel composition where I want to run several tasks in parallel and respond when either one of them or all of them is completed, I can use task.whenAny or task.whenAll. All right, last demo. You guys have hung in there. It's early. It is early. Does this work for you guys? Is this good? Yeah, I see nods. Okay, so there's light bulbs going on. That makes me feel good. All right. So for cancellation, we've seen a lot of ways that you can get results and exceptions back from these future objects from operations. But sometimes you need to be able to communicate with an ongoing operation, with an operation that's already executing. So for example, maybe I don't need the result anymore in my application, or maybe the users hit a cancel button. I need to be able to tell those operations that, hey, bail, stop doing your work. This is a waste of time. And so we're going to take a look at how we do cancellation using Async. All right, so back to this create mosaic async. This guy can actually take quite a while. So it's a great candidate for cancellation. Okay, if I'm going to introduce some cancellation UI, and we're going to do that, this is the kind of method that I want to be able to say, stop doing your work, so that we don't have to wait all the way till the end of it before the cancellation actually occurs. So if I look at this signature, I see there's actually an optional parameter at the very end of type cancellation token. And the cancellation token is this. If you think of task as sort of the first class notion of ongoing work in .NET, you can think of cancellation token as kind of the first class notion of cancellation. It's actually how you represent that I might want to cancel this in the future. So you can create a cancellation token. You can have a cancellation token, pass it to lots of different operations, and that just kind of represents it. Says, hey, I might cancel this, so be sure to be prepared to cancel your work if you see this thing happen. I think of cancellation tokens as these little light bulbs that I pass out, and if they light up, then that causes the operation to go, oh, hey, you're lit. It's time to stop. Okay. So I would pass a cancellation token here. I'd pass it to all the operations that I care to cancel. Okay. Then I'd signal cancellation, and these tokens would light up, and all the operations would cancel. So we're going to do that. We need to get a cancellation token first, and the way I do that, I'm going to put this at the class level, and you'll see why in a moment. And I'm going to create a cancellation token service. All right. And so, I'm sorry, cancellation token source. And what that is cancellation tokens are these light bulbs. That's the big red button. Okay, that allows me to trigger the cancellation of all of these tokens and be the one to do the signaling. That means that if I pass cancellation tokens out to various operations, they can't do the canceling. I'm the one that does the canceling. I'm the one that owns the control. Okay, so if I come in here, right before I start my flow, I'm going to create my cancellation token source. And when I'm done with my flow, I'm going to go ahead and set it to null. Now remember, this is all happening on the UI thread. Even though we're being asynchronous, it happens on the UI thread. So I have kind of an implicit lock here. It's okay that I'm doing this in this manner. All right. Again, it's this sort of style of programming that we're comfortable doing when we're in a synchronous world, and I can also do that with async in an asynchronous world. All right. Now that I've got this cancellation token source, I can go ahead and I can pass the token to my create mosaic async. All right. There's a couple other places I probably want to pass this. This one can also take a while. Fetch images async. And let's see, does it have a, yes, it also has an optional cancellation token. Pass that there. Here's another place where I might want to do this, and you'll find that because cancellation token is a notion in the .NET API, that a lot of the .NET task returning asynchronous APIs also will have overloads that take cancellation tokens. And in this case, it certainly does. All right. And then finally, I'm going to want to pass it here. I'm going to want to pass it to my own method. And unfortunately, I haven't actually added that parameter, so we'll go do that. And so I'm just going to add my cancellation token parameter. We'll call it cancel. And we're going to make it optional. So we'll set it equal to a default of cancellation token. Now this is a struct. Okay, it's a value type. So this essentially says if you don't specify a cancellation token, you get the zeroed out sort of version value type of the cancellation token. And that version of the cancellation token simply doesn't do anything. Like if the operations ask it to be, should I cancel now? It's like, nope, no reason to cancel ever. So that's okay. And we can come down here now. And suppose I now want to say, well, this open async method, again, this could take a long time. It could be SkyDrive, right? I might want to cancel it. So I come down here, I hit comma, or this is a WinRT API. And WinRT does not have the notion of cancellation tokens. Okay, that's very much a .NET task parallel library idea. So what am I to do? I mean, actually, WinRT has a different way of doing, does have first class cancellation, but you call it from the operation directly. So I would take the operation and I'd call .cancel on it, which is a little weird, right? I've been going along here and kind of treating everything the same, and it's been very, very nice that I can treat these WinRT future objects, these .NET future objects the same, and have this unified programming model. And so this would be kind of a breakdown in that, and you would all throw rotten fruit at me if that were the case. So that's not necessarily the case. Instead, what we want to do with this is we can wrap this in a task. This is another case where you'd want to use as task to wrap the operation in a task, and then there is an overload that takes a cancellation token. Okay, so I can pass that in here. All right, so we're almost done with this. We've gone ahead. We've passed cancellation tokens everywhere, but there are two things we need to do yet. We need to be able to deal with what happens when things are canceled, like in the UI from this point, and we need to actually, hook up the UI events, the UI, to perform the cancel. So the way cancellation works is that it actually throws an exception. That's the easiest way to kind of get out of everything. And if we're, if there are things are happening on background threads and all of that, the exceptional control flow is really the way to handle this. And so, since we've already got a catch handler right here, we can go ahead and handle operation canceled exception. Okay, and so when one of these operations get canceled, I'm just going to go ahead, go to the item list view, and set the selected item to null. Not very metro of me, but it's a demo. Calm down, all of you. Getting way too excited out there. All right. Now, let's hook up the UI to actually do the cancellation. And so we're going to use that go back button that appears in the Metro UI, the arrow that goes left. We're going to use that to cancel the work. So in here, I can say, if I have a cancellation token source, and it's not null, then I can go ahead and I can cancel. And I'll set it to null when I'm done. All right? So let's see if this works. All right, so I'm going to go here. I'm going to pick Drew again. And now I can click back while it's calculating the mosaic. And it canceled. It's done. All right. That wasn't too hard, was it? So what's great about async is it kind of gives you this way that you can pay as you go. While we go with while we made it very easy to do asynchronous programming, I really think we have. We also have opened up a new set of challenges for you. Some of you who have done asynchronous programming and background thread work and have pulled your hair out late nights debugging stuff have already thought of the problems of like, well, Dustin, doesn't this mean that I have to deal with reentrancy? And yes, you do. That is one of the challenges of doing asynchronous programming. Yes, you need to think about reentrancy. You need to think about cancellation, progress, all of those sorts of things. But those are good problems to have. Right? So we like to say, my good friend Alex Turner, he likes to say, with great responsiveness comes great responsibility. Right? And so being able to deal with those challenges is a good thing. Because now your app is responsive, your users are happy, and you're making money. And then you're happy, and everything's happy. All right. Let's get back to slides. So, just to kind of summarize cancellation and progress, these are the things we can use to be in contact with ongoing operations. So we can pass cancellation tokens to send cancellation. We kind of push that out to the operations that are in the future objects running. Or we can pass an iProgress, which I'm not going to dig into today, to receive progress updates. So you can have your operations take iProgress and update that so that you can show progress in the UI. And then, most of the async APIs take cancellation tokens. They take iProgress. If you're with a Windows RT, Windows runtime operation, you can call as task and get the same functionality. All right, so we're kind of getting close to the end where I want to take some questions, but just some further reading and documentation. If async is new to you, if your brain hurts right now, if you're like, ugh, Dustin, this was far too simple. I'm really, really smart about this stuff. I'm going to go off and I'm going to read up and I'm going to come back and school you. That's fine. You can do that. It's not hard. Trust me. Go to msdn.com/async. Learn about the project. Download some really cool, more technical information. You can also check the what's new for the Visual C# and Visual Basic languages for VS 2012 RC and find out a lot of great stuff about async there as well. Also, you can go to my friend John Skeet's blog, and he's got crazy stuff about async. So what I want to really leave you with, and this is kind of the thing that I want to really drill home with you, is that we've really set out with async to remove callbacks completely. We really tried to envision a world where you didn't have to write any callbacks, but you could do your normal control flow, your normal sequential control flow, and get the same behavior, but get all that responsiveness and goodness that asynchrony brings. So, and I think we kind of pulled it off, so no more callbacks. All right? Thanks very much. So, I think we have some time for some questions. If anybody has any questions. Yeah.
Is there a downside to it? In the ASP.NET application, should you use it on every database access?
So the question is there, in an ASP.NET application, should I use this on every database access, on everything? I would use it where it makes sense, right? I want responsiveness for my application. If you're experiencing, like on an ASP.NET application, if you're experiencing like I click on that database access and it's not asynchronous already and it's taking a lot of time, then yeah, you might consider doing something like this. But use your better judgment. How does your application run? Is it the right thing to do? I wouldn't just go out and just wholesale add awaits everywhere, because there is cost associated with hooking up lambdas and callbacks, right? That does, that does have some cost associated with it. So I would just use your better judgment. All right? What happens to exceptions when you have fire and forget tasks? Well, it's actually different, I believe, and so I hope I'm not going off on an incorrect place here, because this kind of changed a lot during the design. But in .NET 4.0 with the task parallel library, you have an unobserved exception and the whole process comes down, right? My understanding of where we landed with this with 4.5 is that it's simply swallowed. And because we don't care about what happens to that fire and forget method, after all, we call it fire and forget, so the exception, even if unobserved, is not, does not, because we're not wrapping it up in a task, it's not observed, right? And so in that case, it just gets left on the floor. That's my understanding. So it was kind of a hard problem to solve. So, yeah. Absolutely. So the question was, with cancellation, do you have any control over where in the code the exception may occur? Yes. And so what you do with the cancellation token in your operation is you take the cancellation token and at key places in your operation where you want to be able to say, I'm ready to throw a cancellation exception if cancel has been triggered. And you just say cancellation or cancel or whatever, cancellation token dot throw if canceled. And so it's up to you writing the operation, writing that work to be done where cancellation should occur. You're the one that knows where the best places are. So, this one first.
You mentioned in your talk that you have to take care of the entrancy when you're using await.
Yep.
But on the other hand, you also said that when you're doing await, it kind of you implied that it gets dispatched to the UI thread, original thread rather. So that logically there is no
So the question is, he's calling me out here. He's saying, so I said in the talk that, there's one of the big challenges is going to be, you have to think about reentrancy, right? However, I also said that everything's happening on the UI thread, so of course there is no reentrancy. But it's not quite the case, right? Because you still have reentrancy in the fact that UI events can happen while it's awaiting something, right? So if I go and click on something else, while that happens, and I might not be ready for it, now my code can, maybe it's not that method that can be re-entered, but something else can happen. Okay, and so I need to guard against that. So the sorts of things that we all kind of get when we're doing when I'm doing a WinForms app and it's synchronous and I'm just kind of being sloppy, I don't go and disable all the buttons that I don't want to be clicked at some particular moment. You kind of have to think about those things when you're doing this work. Does this make sense? All right, you had one. So the question is, exceptions, are they expensive as a normal exception? I'm not sure what the numbers are. I think they're about equivalent. Exceptions are expensive in general to hook up the exception handlers. And so, in this case, there's more happening. There are more exception handlers because it's catching those exceptions, resurfacing them in the tasks themselves.
A way to catch the cancellation without an exception. So where I watch for a flag to be set or
and so the other question, the follow-up was, is there a way with cancellation to handle that without catching exception? No, there's not. That's just the way to do that, because you don't know where that is happening, right? You don't know if it's coming back or if there's something I could try. It could be on somewhere else completely, and throwing an exception is the only way to get it to bubble up naturally up the call stack. You can do your own flags. You can do your own thing, right? If you want to use cancellation tokens, though, it's exception driven. Okay. Anything else? You again? Yes, sir.
Can I, for example, when you're using a file, and you want to put that in the database, can you say, I want no more than 10 tasks?
So the question is, if I'm reading from a file and I want to put that in a database, so I assume you mean like lots of files. Read again? Can I do like no more than 10 tasks? Yeah, absolutely. Absolutely. I mean, you have complete control. You can say, I'm going to line up 10 tasks and decide which ones I'm awaiting or ending. Not specifically. So the way, there's not specifically some kind of feature to do that. Async is really kind of this, a little closer to, it's not this grand higher level thing, but it's a lot of components that we expect other people to go and build higher level concepts on top of. You saw that we only really have a few key, for example, task combinators, for example. We totally expect people to go off and build higher level abstractions over those things. We also expect people, with the question with reentrancy, we certainly expect there to be UI frameworks that pop up that rethink reentrancy, build themselves upon async, and kind of manage that work for you. So there's nothing built in, but you can certainly build it with async. Okay? I'll come back. Oh, one here. Yes?
If I have many things to do async,
Mm-hmm. Yep. Yes. So the question is, if I have a bunch of work that I want to do in parallel and I don't care when they come in, I don't care when they finish, well then, I mean, but I want to know when they're all finished, well that's the task.whenAll, right? So you would use tasks and you would pass that to task.whenAll, and that would give you a task back that you could await that would complete when they all complete. Okay?
one other question. Earlier preview, not from this, was the task parallel library. There was an option that I can do some work in the background, and I continue in my code, and the first time I used this object, the code stopped if it's not finished, the background code. If the background is finished, is there something possible now?
Certainly. I mean, isn't that so? The question is, let me see if I phrase it right, and you correct me if I miss it. So if I have some background work, I want to kick off some background work, and then there used to be a feature you said in the TPL where I could stop it and finish that background work. You're thinking like a thread.join kind of thing, right? That's effectively what await is, right? It's saying here, come back here when it's done, right? But stop the execution of my method at this point. So I mean that's await. That's what you're looking for, I think, if I understand your question. It might require some refactoring on your thinking, but okay, that works. Let me get back here real quick before I run out of time. Yeah. I said a lot of things.
Most of the async method calls had an override that accepted a cancellation token and maybe even a progress.
Mm-hmm.
The methods that don't, are they non-cancelable, or can you do ask task?
I may have said most not being qualified. They may all have them. I didn't. Yeah, I wasn't implying that. Oh, there's a few secret methods that are really important to you that don't. No, that wasn't my implication. I just used the word most a lot because, yeah. There was a question over here. Yeah. When I start a task, can I cancel a task? So the exception winds up in the task itself. The task object can handle. So the question was, you know, if I understood it correctly, the question was, you know, prior to task with a background thread, the exception gets thrown. It winds up in the IL, right? How does that work with tasks? And with tasks, it doesn't necessarily get thrown. It gets wrapped up. It gets caught by, well, it doesn't get thrown, but it gets caught by the state machine. It gets stuffed into that task, all right? And so the task says, instead of being a successful completion, and here's a result, it says, no, I actually completed, but I was in an accepted state, and here's the exception. And so you can get the exception. If you want to get the exception directly from the task, you can do that.
I mean, if you cancel the task,
Uh-huh.
do you have to check everywhere if the token is set, or does exception thrown automatically somewhere?
I see. So the question was around, the question was around cancellation, right? Do I have to check everywhere, right, to say, oh, is the exception being thrown? No. You don't have to Again, it's a pay-as-you-go kind of thing. If I want to write an operation and I don't care about cancellation, I don't have to check everywhere. I can stop and do. But you never have to check everywhere. You can handle it at a higher level, like I did here, and say, okay, the operation was canceled, and I'm okay to go. If I understand what I'm not sure if I'm answering your question though, because I'm not sure if I understand the kernel of it.
I create a task and I do a lot of work.
Right. You create a task and you do a lot of work. Okay.
I get a cancellation token.
Uh-huh.
Do I have to check the cancellation token inside my code?
Oh, do you have to check the cancellation token inside your code? Or does it do an automatic cancellation? Yes, you have to check it inside your code. So it gets back to the answer to this gentleman over here, where it matters that I'm the one that knows where in my code I should be checking cancellation. There might be places where it's not safe to cancel. Right? It might be not, I might put my code in some crazy state. I might destroy some data structure by just throwing an operation cancel exception. So at the logical places in your operation, call cancellation token.throw if cancel. Okay? What time is it? I just want to make sure I'm not keeping you guys too late. One more. We got 1 minute. You're the one. When the task is created, does it create a physical thread? It does not create a physical thread. Okay? So again, the idea is that we are scheduling work for later and returning to the UI thread, and there's no thread that's scheduled to kind of watch that. All right? So, and especially with this network-bound work, I/O-bound work, no threads get scheduled. We just go off to the OS, make calls, and wait for those to come back. Those come back and trigger an interrupt in the message pump, right? As opposed to us going off and creating a thread to try and watch a thing. So no, async is designed to avoid creating threads if possible. What's that? So when I did the background thread piece, so again, it's a situation where if I need to create background threads, that's me doing that, right? That's me saying task.run to say, okay, I want this to run. And it's actually running on the .NET thread pool, right? So if there are threads available on the thread pool, it won't create a thread either. But that's my control. That's in my control as a user. Async doesn't create threads for you under the hood. All right, guys. I think that's enough for questions. If you want to hang out and chat later, that's fine. But thanks very much for coming out. Don't forget to fill out your evals because that helps me speak again. And thanks.